Hello YouTube, this is Wenn who does research for fun. In this video, I would like to go over my very first authored paper titled Weed Height Estimation using LiDAR in comparison to ultrasonic sensor and UAS, which was published in the journal Sensors in 2018. The research project for the paper originated from an observation by my master's advisor, Dr. Yu that at the time, no study directly compared the plant height estimation methods that we were interested in for field crops. We collaborated with two research teams and conducted a field experiment to fill this gap. This paper introduced me to the world of research and publishing, a journey I haven't stopped ever since. It also happens to be my most cited paper, despite arguably being one of my least technical papers. It was initially submitted to a different journal, but was instantly rejected by an editor and did not even make it to the reviewing stage. I'm glad it was eventually published so that I can share it with you here. Let's dive right in. Field phenotyping is a branch of phenotyping, which refers to the process of measuring and analyzing observable field crop traits. Given a plant, field phenotyping might characterize its morphological traits such as height, width, volume, biomass, and leaf angle. Its physiological traits such as temperature, water content, and stress level. And its temporal traits such as growth rate, stem angle trajectory, leaf curvature rate, germination time, and senescence time. Among the observable traits, plant height is a key parameter in crop breeding. It has been observed in literature to be associated with yield, lodging, biomass, disease resistance, etc. Traditionally, plant height is manually measured, such as by using a yardstick, which can be labor-intensive, time-consuming, and prone to error, especially when a large number of plants need to be measured in the field. To address this issue, researchers have developed high-throughput multi-sensor systems that can simultaneously and efficiently measure multiple plant traits, including height, using sensing technologies, so that breeders no longer need to spend hours under the scorching sun on a humid summer day to manually collect data. I've been there. At the time, some of the notable systems included Breed Vision by Boosmeyer et al. In 2013, an unnamed system by Andrade Sanchez et al. In 2014, Phenomobile by Deary et al. In 2014, Field Scanalyzer by Verlet et al. In 2017, Ladybird by Underwood et al. In 2017, and Phenomobile Light by Jimenez-Burney et al. In 2018. I'm sure more systems have been developed since. On a typical field phenotyping system, there are two types of sensors that are commonly used for plant height estimation. The first one is ultrasonic sensor, which measures distance based on sound waves and the time of flight principle. Ultrasonic sensor is inexpensive and user-friendly. However, it is less accurate for farther objects due to the larger footprint. It is sensitive to temperature as sound speed changes with the temperature, and it is susceptible to irregular shapes such as plant structures, which might not create strong enough echoes. The second one is LiDAR. The first generation LiDAR technology measures distance based on laser and the time of flight principle. It can create point clouds with high spatial resolutions, since lasers have low beam divergence. It is also an active sensor that does not require external illumination. However, LiDAR is typically pricey and generates large volumes of data, which can be challenging to process. In addition to ground-based systems, UAS, or Unmanned Aerial System, at the time emerged as another popular tool for field phenotyping. A UAS is essentially a UAV or drone equipped with mission payloads such as cameras. By capturing overlapping images of a field and feeding the images into a photogrammetry pipeline, 3D point clouds of the field can be reconstructed, and field geometry information, including plant height, can be further extracted. UAS offers very high throughput and can scan large areas within minutes. It also provides great temporal and sensor flexibility, meaning that flight missions can be conducted at almost any time and various onboard sensors can be easily integrated. However, UAS usually has a limited payload capacity and flight duration. For manual flight missions, pilot proficiency is required. In the existing literature at the time, in terms of plant height estimation, ultrasonic sensor had been applied for cotton, alfalfa, wild blueberry, legume grass, Bermuda grass, barley, and wheat, and R-squareds of 0.44 to 0.9 were achieved. LiDAR had been applied for corn, sorghum, and wheat, and R-squareds of 0.86 to 0.99 were achieved. UAS had been applied for cotton, blueberry, and wheat, and R-squareds of 0.27 to 0.99 were achieved. Here we can see that LiDAR seems to demonstrate superior performance over the other two methods. However, to conclude which method is the most accurate, a direct comparison between the methods within the same experiment against a common ground truth would be necessary, which was missing in the existing literature at the time. Because of that, the objectives of the study included first, develop a LiDAR point cloud processing method to extract plant height information based on the static measurement style adopted by our ground phenotyping system. And second, compare ultrasonic sensor, LiDAR, and UAS in terms of plant height estimation performance. The study was conducted at Havelock Farm of University of Nebraska-Lincoln, about 5 miles northeast of the East Campus. The field experiment included 100 wheat plots arranged in an augmented design, consisting of 10 track varieties replicated twice and 80 unique genotypes. The wheat plots were measured or scanned by 3 methods independently. The first method was the traditional agronomic method by manually measuring height with a yardstick. During each data collection session, 3 manual measurements were taken for each wheat plot and averaged as a reference height. For vegetative growth stages, wheat height was measured by method A, from soil surface to the top of stem. For reproductive growth stages, wheat height was measured by method B, from soil surface to the tip of spike excluding awns. The second method was a ground phenotyping system equipped with a LiDAR and 3 ultrasonic sensors to scan 3 wheat plots simultaneously. The third method was UAS equipped with RGB cameras. In total, there were 5 data collection sessions throughout the 2018 growing season. This table shows the wheat growth stages and the data collection dates of the 3 methods. The ground phenotyping system was a custom-designed phenocart, constructed using 2 bicycles for movement and steering in the field, with a central platform carrying essential equipment including a data acquisition box, a battery, and a laptop, and 4 sensor bars mounted to the frame for holding the sensors. The system had 3 down-looking sensor bars and 1 up-looking sensor bar. All 3 down-looking sensor bars were equipped with an ultrasonic sensor, an optical fiber, a camera, and a radiometer to scan 3 plots simultaneously. The middle down-looking sensor bar, however, as shown in the image on the left, was equipped with an additional LiDAR. The up-looking sensor bar was equipped with a temperature and relative humidity probe with a solar radiation shield, an optical fiber with cosine corrector, a GPS receiver, and a pyranometer. The cable harnesses from the 4 sensor bars were connected to the data acquisition box, which contained a power supply circuit, a DAQ device, a USB hub, and 4 spectrometers. Data communication-wise, the radiometers, ultrasonic sensors, temperature and relative humidity probe, and pyranometer transferred voltage signals to the DAQ device. The optical fibers transmitted light signals to the spectrometers. The DAQ device, spectrometers, cameras, and GPS receiver sent signals to a USB hub via USB. And finally, the USB hub and LiDAR were directly connected to a laptop via USB and Ethernet, respectively. The entire system was controlled by a custom LabVIEW program, which allowed for sensor configuration, real-time sensor output display, and data collection triggering. This image shows the front panel or user interface of the program, while here is a sneak peek of the block diagram of the entire program and the block diagram of a sub-VI within the program just for processing raw LiDAR data. The program followed a straightforward logic. It first initialized and configured the sensors, then read sensor signals once per second in a while loop, while simultaneously checking whether the measure or stop button was pressed. If the measure button was pressed, it saved the sensor readings to a file. If the stop button was pressed, it exited the program. Here is a live demonstration of the system operation. The person in the video was a PhD student named Sean that I used to work with for soybean studies. One of the nicest people I've ever met. I used to call him Superman because he could hook up a heavy trailer to a truck's ball hitch with a single hand, while the rest of us needed at least 2 people or 4 hands to do the same. He could work all morning non-stop on a hot, humid summer day, and for lunch, he would just eat a tiny bag of goldfish crackers and be ready to go again, while I was dying of heat exhaustion in the car with the AC blowing full force at my face. I hope he's doing well. As mentioned previously, the ground phenotyping system could scan 3 plots simultaneously. Each ultrasonic sensor was responsible for 1 plot, and the LiDAR was responsible to measure 3 plots at once. The figure here shows the approximated sensing areas of the ultrasonic sensors and LiDAR, and a relevant concept, plot width, which was defined as the distance between the centers of 2 adjacent alleyways. The ultrasonic sensor employed in the phenotyping system was Ultrasonic 14 from Senix. It had a 14-degree field of view, a maximum measurement distance of 4.27 meters, output a 0 to 10 VDC signal, and was configured with a 20 Hz measurement rate. To calculate crop height measured by the ultrasonic sensor, its voltage signals were first converted to distance values using a lab-calibrated equation. And crop height was calculated as the difference between sensor to ground distance and sensor to crop canopy distance. Each ultrasonic sensor provided 1 height value for each read plot at each data collection session. The LiDAR employed in the phenotyping system was the iconic PUC, or VLP-16 from Velodyne, which has since merged with Ouster. It featured 16 near-infrared lasers, a 903 nanometer wavelength, a 100-meter maximum measurement distance, a 30-degree vertical field of view with a 2-degree resolution, a 360-degree horizontal field of view with adjustable 0.1 to 0.4 degree resolutions, and was configured with a 180-degree horizontal field of view with a 0.1 degree resolution and strongest return. The raw LiDAR data packets only contained azimuth and distance information of all 16 lasers, which needed to be converted into 3D point clouds first, before further processing. The 3D Cartesian coordinate system was defined as shown in the figure, with its origin aligned on the ground vertically below the sensor center, its x-axis pointing towards the sensor side, and y-axis pointing towards the sensor top. After obtaining a 3D point cloud, its points beyond the 3 scanned plots were removed using 2 thresholds of plus minus 1.5 times plot width along the x-axis One of the issues that we frequently encountered in the field was the slanting of the phenocart, along with the sensor bars, due to the unevenness and slope of the ground. As a result, the LiDAR 3D point clouds appeared to be tilted in the 3D Cartesian coordinate system, which affected extracted plant height accuracy. To compensate for this issue, we proposed a LiDAR point cloud pre-processing method by assuming the ground slope variation between the 3 scanned plots within LiDAR's horizontal field of view could be ignored. The pre-processing method first fits a linear least squares curve to a point cloud's YZ plane, converted the curve slope to an angle, and rotated the point cloud in the opposite direction of the slope by the angle so that the point cloud became level. This step assumed point cloud without the slanting issue would be evenly distributed along the y-axis, considering plants with the same genotype should have similar heights. Since point distribution along the x-axis cannot be assumed even, as the points could represent plants in different genotypes with different heights, linear curve fitting couldn't be directly applied to the XZ plane. The second step involved sorting points by their x values, applying a moving average filter with a 0.05 meter span to smooth the curve, finding 4 positions C1, C2, C3, and C4 with the most significant changes, and segmenting 2 point clouds containing alleyway points in between C1 and C2 and C3 and C4. In the third step, the z-value kernel density and the first derivative of the kernel density curve were calculated for each alleyway point cloud. Assuming ground points followed a normal distribution along the z-axis, the first peak in the kernel density curve P1 represented the mean of the distribution. The first peak in the first derivative curve P2 represented the inflection point of the distribution, and the standard deviation of the distribution was subsequently calculated as P1 minus P2. Finally, the threshold of mean plus 2 times standard deviation was used to separate ground points from non-ground points, which should contain more than 95% of the ground points. After combining the 2 alleyway ground point clouds, in the fourth step, a linear least squares curve was fit to the point cloud's XZ plane, and the point cloud was rotated accordingly based on the slope of the curve. In the fifth step, the average z-value of the combined alleyway point cloud was calculated, and the entire point cloud was shifted accordingly so that the average alleyway point z-value set at 0. In the sixth and final step, the average x-value of the 2 alleyway point clouds were calculated respectively, and used as 2 borders to split the point cloud into 3 sections for the 3 scanned plots. All point cloud processing was completed using MATLAB R2017A in the study. Since the agronomic methods did not simply measure the tallest point of wheat plants, optimal point cloud percentile heights that corresponded the best to the agronomic methods needed to be investigated. In total, 200 height values were extracted for each wheat plot and each data collection session using 0.5% intervals from the 0th to the 100th point height percentile. For UAS data collection, 2 systems were used due to hardware availability. The first one was Matrice 600 Pro with Zenmuse X5R, which had a 4608 by 3456 resolution. The second one was Phantom 3 Professional, which had a 4000 by 3000 resolution. During the flight missions, Matrice 600 Pro and Phantom 3 Professional flew at a 20 and 15 meter above ground level respectively to maintain comparable ground sampling distances, which were 0.47 to 0.67 centimeters per pixel. The forward and side image overlaps were set at 88%, and 21 black and white cross-centered wooden boards were evenly distributed across the field, measured by an RTK GPS and used as ground control points for orthomosaic georeferencing. For image processing, the software Pix4D Mapper was used to generate digital surface models, and the software ArcMap was used to manually and uniformly delineate the individual weed plots and create digital terrain models by applying kriging interpolation over the soil pixels extracted from the digital surface models. To extract plant height maps were first calculated by subtracting the digital terrain models from the digital surface models, and in total 100 height values were extracted for each weed plot at each data collection session using 1% intervals from the 0th to the 100th pixel height percentile. For data analysis, we first compared the heights extracted from the raw and pre-processed LiDAR point clouds correlated with manual measurements in terms of minimum RMSE and optimal point height percentile. Here we can see that the pre-processed point clouds consistently had lower minimum RMSE than the raw point clouds across all data collection sessions by 13 to 45%. For the first and second data collection sessions, when the agronomic method A was used for vegetative weed growth stages, they also had substantially different optimal point height percentiles than the rest. This figure shows how well the heights extracted at different LiDAR point height percentiles correlated with the manual measurements in terms of RMSE, bias, and R-squared. Generally, low point height percentiles represented ground, while high point height percentiles represented weed canopy. Therefore, it made sense to see all three metrics generally became better as the percentiles increased, but became worse as the percentiles approached 100%, since the agronomic methods never measured the tallest weed plant points as the final height. At the percentiles of the minimum RMSEs, the average bias over the 5 data collection sessions was negative 0.0011 meters, which demonstrated LiDAR's accuracy. The percentiles for the maximum R-squareds fluctuated between 98 and 99% across all data collection sessions, which interestingly did not agree with RMSE and bias for the first 2 data collection sessions, where we can see that the optimal percentiles for the minimum RMSEs and biases were much lower. Apparently, when data collection was conducted on different dates, the optimal point cloud percentiles could always change, as the weed plants were continuously growing and their structures were constantly changing. To establish a practical and reasonably precise method, we classified the data collection sessions based on their corresponding agronomic methods. Here in this table, we can see that the overall minimum RMSE, without making the distinction between the 2 agronomic methods, was 0.0657 meters, which was 37% and 65% higher than the minimum RMSEs of agronomic method A and B categories respectively. Therefore, it makes sense to adopt different point height percentiles for different agronomic methods. Additionally, we investigated the effect of plot position, because the closer a plot was to LiDAR, the denser the plot point cloud would be. In our case, each LiDAR scan included 2 side plots and 1 middle plot. On average, the side plots had about 6,000 points, while the middle plot had about 8,000 points. In this table, we can see that plot position did not affect minimum RMSE in a major way, with an average minimum RMSE increase of 0.0026 meters when plot positions were not differentiated. Therefore, the effect of plot position was considered to be insignificant. For UAS, it was observed that the 89th pixel height percentile provided the lowest RMSE for agronomic method A, with a 0.0439 meter RMSE, a negative 0.0035 meter bias, and a 0.897 R-squared. And the 100th pixel height percentile provided the lowest RMSE for agronomic method B, with a 0.1086 meter RMSE, a negative 0.0702 meter bias, and a 0.436 R-squared. This figure shows the correlations between the manual measurements and the estimations from ultrasonic sensor LiDAR and UAS across all 5 data collection sessions, based on the optimal point height and pixel height percentiles as mentioned previously. LiDAR achieved the best overall performance with a 0.05 meter RMSE, a negative 0.02 meter bias, and a 0.97 R-squared. UAS achieved the next best overall performance with a 0.09 meter RMSE, a negative 0.04 meter bias, and a 0.91 R-squared, but it tended to underestimate weed height, and its estimations tended to scatter more as weed plants grew taller. Ultrasonic sensor did not achieve a good overall performance, with a 0.34 meter RMSE, a negative 0.22 meter bias, and a 0.05 R-squared. It overestimated weed heights for the first data collection session and underestimated weed heights for the rest of the sessions. Additionally, negative height estimations can be observed in the figure as well, which will be explained next. The poor performance of ultrasonic sensor could be attributed to 3 factors: sensor limitations, weed morphology, and measurement style. When sound waves are not reflected straight back due to either sensor or object surface orientation, ultrasonic sensor may not capture the reflected sound waves. In our case, the phenocard slanting issue could be causing that. When the surface of an object is not large enough to create strong echoes, ultrasonic sensor may not treat the weak echoes as valid signals. Weed plants typically have narrow leaves and thin spikes, which are more likely to create weak echoes than strong echoes. Because of our static measurement style, the ultrasonic sensors were only able to sample a small area within each plot, about 0.05 square meters, assuming a 1 meter distance between sensor and weed canopy, which could lead to biased height estimations due to within plot height variation. A few ultrasonic sensor height estimation anomalies were observed in the study. First was the height over and underestimation, which is illustrated by this figure. For a young weed plant, clustered leaves with a natural curvature seemed to reflect sound waves quite effectively, but the manual reference height was measured as the height of stem top instead of leaf top for the ergonomic method A, leading to the height overestimation. As weed plants grew taller and their spikes emerged, only the vegetation at the bottom of the plants seemed to have sufficient density to reflect strong echoes, while the manual reference height was measured as the height of spike tip for the ergonomic method B, leading to the height underestimation. Second was the near zero or negative heights. Near zero canopy heights could be recorded when ultrasonic sensor could not detect any significant echoes except for those reflected from the ground. When that happened, if the phenocard was also slanted or the ground surface was uneven so that the distance between the ultrasonic sensors and ground was larger than the initial sensor to ground distance, the negative canopy heights could be recorded. To improve height estimation accuracy by ultrasonic sensor, a continuous measurement style where multiple measurements are recorded per plot can be adopted. In existing literature at the time, researchers have achieved a 0.046 meter RMSE with roughly 180 measurements per plot and a 0.85 R with 25 to 30 measurements per plot. However, the potential downsides of that include first, inconsistent numbers of height measurements can be recorded for different plots, since the phenocard speed can be highly variable in the field. Second, repeated measurements of the same sampling areas could be taken when the phenocard needs to be stationary, such as during camera image acquisition. Both can cause difficulty for subsequent data analysis. Just like ultrasonic sensor, 2 types of height estimation anomalies were also observed for UAS. The first one was height underestimation, which became more severe after the second data collection session. This issue could be possibly caused by insufficient camera resolution for capturing weed spike details and reconstructing weed spike point clouds. Therefore, the plant height maps did not truly represent wheat spike heights. The second one was scattered height estimations. During our later data collection sessions, there was pretty strong wind in the field. Wind had no influence on manual measurements, as the wheat plants were held by hand when measuring, but it caused a large plant movement during UAS data collection, which only got worse when the plants were taller. Inconsistent plant positions among images could reduce mosaic quality, therefore leading to higher digital surface model errors. Generally, UAS-based plant heights are calculated by subtracting digital terrain model from digital surface model. However, the exact methods vary among studies. Digital terrain model can be generated by either interpolating soil pixels from digital surface model or scanning bare soil before seedling emergence. For plant height determination, researchers have adopted average, 99.5th percentile, and 100th percentile pixel values within each plot delineation in plant height maps. The results achieved in our study was comparable to existing wheat studies at the time, such as 0.92 r², 0.88 to 0.98 r, and 0.99 r², and 0.031 meter RMSE. For improvements, decreasing flight altitude to achieve higher image spatial resolution can be a strategy, but at the cost of longer flight time. Directly extracting plant heights from reconstructed point clouds, which could contain higher quality plant 3D information than rasterized 2D digital surface models, might also provide better results. For LiDAR, our proposed point cloud preprocessing method effectively mitigated the phenocard slanting issue. However, since this method utilized alleyway ground points to rotate point clouds, configuring LiDAR in dual return mode, meaning each laser firing could receive up to 2 signals instead of just 1, can help increase the chance for LiDAR to capture ground points, even when vegetation is dense. Wheat growth stage certainly affected LiDAR performance, and its influence was reflected in 2 ways. First, the optimal point height percentiles increased with wheat growth stage. That is mainly because of the ergonomic manual method change, from measuring stem top in method A to measuring spike tip in method B. Second, minimum RMSE increased with wheat growth stage, and that could be possibly explained by the larger degrees of plant bending due to wind as the wheat plants grew taller, and LiDAR could capture deformed point clouds that did not reflect true plant heights when they stood straight up. During our last data collection session, for example, the wind speed in the field maintained at 8 to 9 meters per second, and gust speed was up to 15 meters per second. There are a few general steps for extracting plant heights from LiDAR point clouds. However, the exact methods for each step vary among different studies. The first step usually involves soil level estimation, because soil height serves as a baseline for plant height to be referenced to. And researchers have utilized a point cloud z-value histogram peak, non-vegetation point mean height, vehicle wheel contact point, direct soil measurement, which was the case of our study, and assumed sensor to ground distance. Next, as 2 optional steps, noisy points might need to be removed sometimes, as LiDAR can detect spurious points in very bright light conditions. The noisy point removal step in our case would be unnecessary, as such low quantity noisy points would not substantially affect the optimal point height percentiles. Point clouds were also sometimes rasterized into images for simpler data analysis, and plant heights could be extracted in a similar fashion as for the UAV-based plant height maps. Finally, a certain height percentile needs to be selected to extract corresponding plant height, and percentiles such as 95th, 95.5th, 99.5th, and 100th have all been utilized by researchers. The LiDAR performance in our study was comparable to existing pertinent wheat studies at the time, such as 0.9 r², and 3.47 cm RMSE. 0.88 and 0.95 R-squareds, 0.993 R-squared, and 0.017 meter RMSE. 0.86 R-squared, and 78.93 millimeter RMSE. Our study also demonstrated the feasibility of measuring plant height only based on a section of a plot instead of the entire plot. The upside of that is higher throughput in the field, but the downside is lower measurement precision. In comparison to the other two methods, LiDAR has a higher spatial resolution and smaller beam divergence than ultrasonic sensor, while it provides direct measurements but has a lower throughput than UAS. For example, to scan 100 plots, our ground phenotyping system would take about 15 minutes, while UAS only needed about 6 minutes. To improve LiDAR performance, under the context of our static measurement style, collecting more data packets to generate denser plant point clouds might provide better results. Additionally, establishing optimal percentiles for every single weed growth stage could provide much more precise and accurate plant height estimations. In conclusion, our proposed LiDAR point cloud pre-processing method was demonstrated to be effective in reducing uneven ground surface influence. LiDAR point clouds of plot sections were proven to be sufficient for accurate and precise weed height estimation. Ultrasonic sensor was not recommended for height estimation of plants with tall sward structures using a static measurement style, and LiDAR and UAS were both recommended as reliable weed height estimation methods. Looking back at this paper, something I would do differently now is to split the weed plots into training and test groups. Investigate the optimal LiDAR point height percentiles and UAS pixel height percentiles using the training group, and examine the method accuracies using the test group. And probably I would add a more thorough UAS data analysis similar to the LiDAR section and more discussions for UAS. I never presented this paper at a conference because I think at the time I was having pretty bad imposter syndrome. This whole paper in its essence was about measuring height using LiDAR. And I felt like a fraud because I thought there was absolutely nothing complicated about that. In a sense, I was not wrong, but what I did not realize at the time was research is never about being complicated. It is about filling the knowledge gaps that are not known to existing literature. Simple research, complicated research, someone has to do it. Why can't it be me? I know I have been extremely harsh on myself my whole life, so if I can go back in time, I would pat on my back and tell myself, good job. I hope you have enjoyed this video so far. I know I mostly sounded like a robot even though I tried not to, but hey, everyone has to start somewhere. I'll see you in my next paper.